Good morning. Welcome to Grand Rounds. It is with great pleasure this morning I'll be presenting to you this morning's Grand Round speaker, Dr. George Thanassoulis. Dr. Thanassoulis comes to us from Canada. He got his MD at the University of Toronto, which was then followed by residency and a fellowship in cardiology at the McGill University. Following that, he went to NHLBI and spent 2 years at NHLBI working with the Framingham Heart Study. So after that, he returned to McGill, where he is currently an associate professor and director of preventive and genomic cardiology. Dr. Thanassoulis is extremely productive. His research is in the area of cardiovascular disease prevention, but he does it with molecular and genomic approaches, as we will hear. Very interesting studies. Dr. Thanassoulis is productive and published a lot of papers, something like 100 papers in the last 8 years, almost all of which in high impact journals, the likes of New England Journal of Medicine, JAMA, Journal of American College of Cardiology, Circulation, etc. Very, very enviable record. The title of his today's talk is Therapeutics for Aortic Stenosis with genetics or target. I think he'll be telling us about the interesting findings, seminal findings on how he identified the genetic basis of the risk factors for aortic stenosis. So, Dr. Thanassoulis.
Thanks, Mike, for that great introduction, and thank you all for inviting me here today. It's actually my first time in Minneapolis, so it's nice to be here. I've been to Rochester, and we were discussing a little earlier. I've been to other places on the border with Canada, but never to Minneapolis. So it's great to be here. Unfortunately, I have to say I'm a little disappointed with the hockey game last night. I'm not sure if you saw that. Did you see that? Yeah, that's like not the way to treat your invited speaker. I mean, 7-1? Anyways, we won't go there. So anyways, thanks again, and I will be talking about therapeutics for aortic stenosis using genetics. So first of all, I'll discuss a little bit about why I study the genetics of aortic stenosis. So aortic stenosis, as I'll tell you, is it's a pretty common disease, and we know very little about it. And one of the real drives behind my research program was try to see if we can understand this disease, which has kind of been forgotten in cardiovascular disease, a little bit better. We'll discuss the first locus, which we identified in 2013, which is LPA, which is an interest that I share with Mike. We'll discuss a little bit about what we know now about the mechanism and how this is already progressing to a possible therapy for aortic stenosis. And then we'll discuss some more recent work which is unpublished. So in a sense, this is going to be sort of preliminary peer review from this crowd here. We'll discuss a new locus for aortic stenosis, which is the FADS1-2 locus, and we'll discuss whether this also might have potential as a therapeutic target. So aortic stenosis, as I mentioned, is the most prevalent valve diseases in the United States. As you know, most people start. I know there's a lot of pathologists here, so you know this better than I do. But there, the normal. Sorry, here, just getting my bearings on the thing. The normal aortic valve leaflet normally has 3 leaflets that are very pliable and thin, and when this opens, there's very little resistance to flow from the heart. In aortic stenosis, the architecture of the leaflets starts to degenerate. There's calcium deposition, a lot of fibrosis, and then the opening of the valve becomes restricted. And as the valve becomes progressively restrictive, this leads to restriction to flow, and then of course symptoms of patients developing symptoms of heart failure, syncope, and even angina. And for, I'd say, over 40 years, we've just assumed that this transition has been a consequence of aging, and there's probably a number of papers that just call this degenerative disease of aging, and therefore really nothing really we can do about it. This is just a consequence of getting older. And I guess one of the major thrusts of our research program is to question that dogma, that aortic stenosis is a degenerative disease, and there is nothing we can do to prevent the progression of this disease. So we know that the prevalence of aortic stenosis is expected to increase with the aging populations. This is becoming a bigger and bigger problem in North America. So as I mentioned, this has been really thought to be a passive degenerative disease, and what's really striking is in 2018 we have absolutely no medical therapy for aortic stenosis. So I have patients who I will see in clinic. They'll be in their 60s and have mild aortic stenosis, and they'll tell me, "So doc, what should I do about that?" And I look at them with a blank stare, and I say, "Well, try to do whatever you do to keep your heart healthy, but there's nothing specific that we can offer you to prevent this from getting worse." And of course, it's a bit disconcerting to patients to think that they're on the track of eventually requiring open heart surgery, and there's nothing that the medical community can do. Now, there's a very brief period where people felt maybe there was something we can do, and there was a few clinical trials using statins, HMG-CoA reductase inhibitors, to try to lower cholesterol, to try to see if we can prevent this disease. They were all negative, and the reasons for that are probably complicated. We do think that LDL cholesterol and apolipoprotein lipoproteins are probably important in this disease, but most of these trials are done very late in the disease, so it's very difficult to try to prevent a disease when it's already reached an advanced stage, and when most of these trials were performed. So I don't think this necessarily says that all therapies for aortic stenosis will fail. I think it's just a question of finding the right target and also the right timing to try to actually prevent the development of this disease. So our main goal here is to try to see if we can identify genetic loci which associate with this disease, and then use that to try to see if we can then learn from those genetic traits to see whether we can develop therapies that actually mimic the effects of those genetic variants. And one of the interesting things about aortic stenosis, and I like to remind people of this, is because it's a disease that occurs relatively late in life, there's a possibility that if we can delay its onset by 10, 15 years, we could actually make it a disease that we no longer see, or individuals don't require surgery or valve replacement. So it's positioned in a place where I think there's at least potential for preventative therapy. So this is our major finding, which we published in the New England Journal in 2013. We performed, this is actually using data from Framingham, from Mesa, and also from a cohort in Iceland, where we actually looked at valve calcifications. These patients did not have aortic stenosis. These patients had valve calcification on CT, so a subclinical phenotype. These are actually healthy patients who just had flecks of calcium on their valves, which was picked up by CT. And we actually made a bit of a leap of faith there. We said, if we study just calcification on the valve, these little flecks of calcium, could that give us enough information to actually better understand the biologic process that's leading to that calcification? And then could that then be used to then understand aortic stenosis? So very difficult to study aortic stenosis, at least in 2013, because there are very few cohorts that had large enough numbers of cases with aortic stenosis. But valve calcification, because it's a subclinical phenotype, is pretty common. So this allowed us an approach to study this without having to collect large case studies of aortic stenosis. So one of the really nice things about aortic valve calcium is it is an endophenotype, and it's very, very tightly linked with the process of calcification. It has an extremely high signal-to-noise ratio because really on a CT scan, you can really see where the calcium is and whether an individual has calcium, or this person who has quite extensive calcification of their valve versus someone who has less calcium or no calcium. So it's quite easy to see this. And again, because we're studying one process one biologic process, which is calcification. We're not looking at fibrosis. We're not looking at other processes. We're focusing on one biologic process. We theorized that perhaps this was going to be easier to genetically dissect because now we're actually looking at just calcification, and that was the thought behind this study. So this is the result. This is a genome-wide association study. I'm sure you're familiar with this. Just for those who aren't, basically what this is the chromosome position. These are basically it's a case control study. So cases compared to controls for the presence of a variant. This is the chromosome position. Each of these dots represents one single nucleotide polymorphism, and the y-axis here just represents how strong the statistical association is. So the higher the peak, the more different the presence of that variant is in cases as opposed to controls. So what we have here is we identified the one variant, which happened to be on chromosome 6 near the LPA region that was highly associated with aortic valve calcium. Now remember, this is just valve calcium, this isn't aortic stenosis, but it did give us an idea that LPA had to be important in the calcification process. And these are the results, and what was really striking in this study was the size of the association. Now, when we do these genetic studies, we typically see effect sizes that are less than 1.5. So these are usually quite small. These are common variants in common diseases. The effect sizes are quite small. Here we saw an effect size that was a twofold increase in the odds of calcification, which is actually very, very strong. And we saw that across almost all the cohorts. So Framingham, Aegis, Mesa, and when we pooled it, a very strong statistical result with a p-value of 9 times 10 to the negative 10, which is required in these sort of fishing expeditions where we're looking for a statistical signal. When we do all these statistical tests, we really have to achieve a very stringent p-value to confirm that this is actually a true positive. And then we were able to then replicate that, which is also important to just show that there is consistency. And we did that in a smaller cohort, again, with a very, very consistent odds ratio. And when we pooled everything, the results were, again, even stronger as expected. So this showed very clearly that LPA, and this SNP in LPA was associated with aortic valve calcium and the biologic process of calcification on the leaflets. But the real question, as a clinician and a cardiologist, is does this translate to actual aortic stenosis? Is this SNP also associated with aortic stenosis? So to do that, we actually contacted some collaborators in Sweden at the Malmo Diet and Cancer Study. This is a large cohort of 28,000 individuals who had been followed up for over 14 years. And in this cohort, about 1% of the individuals had developed aortic stenosis. So the clinical disease. This was determined by ICD coding. And we also did a sensitivity analysis with aortic valve replacement. So we didn't want to just see whether this was associated with aortic stenosis. We also wanted to get a sense of whether this was associated with severe aortic stenosis that actually required valve replacement. And again, the results were actually quite compelling. When we actually looked at the same variant, so the variant we identified for aortic valve calcium, when we looked at it for aortic stenosis in the second cohort, we saw again a relatively strong association with a 70% increase in the risk of aortic stenosis in Malmo, and we looked at valve replacement, again a 50% increase. So this LPA SNP seems to not only associate with the biologic process of calcification, but also with the clinical endpoints of aortic stenosis and aortic valve replacement. And then we also confirmed this in another 10,000 individuals from Copenhagen, just to really show that this is a consistent finding and a replicable one, and this is a true positive. And what's really exciting, especially as a relatively early career investigator, is how reproducible this association is. We're in the midst of a reproducibility crisis in science, and a lot of findings turn out not to be true, and we have a difficulty in replicating our results. But here, this is a meta-analysis that we published a couple of years ago, and we looked into every cohort that had ever looked at an association with this SNP and aortic stenosis, and the results were extremely consistent. In all the cohorts we looked, the odds ratio roughly was in the 1.6 to 1.5 to 1.6 range. Again, strongly confirming the importance of this variant, and of course the LPA lipoprotein in aortic valve disease. And we also went on and showed that another variant here, 379, which is also an LPA, also was associated with. This is a very rare variant, so the strength of association was a little bit less. Building on that, we then have now created one of the largest cohorts of aortic stenosis right now that probably in the world. We worked with the Kaiser Permanente group in California. They have developed what's called the JERA cohort, which is about 100,000 individuals who've all been genotyped. And what we did is, in collaboration with them, we asked them how many aortic stenosis individuals can we identify in this cohort, and then we were able to start working with this data to confirm the LPA finding, but also look for new variants working with aortic stenosis as opposed to aortic valve calcium. So this cohort, as I mentioned, 100,000 individuals. We used ICD-9 coding to identify AS or aortic valve replacement, and therefore we've created this case control study to study AS in about 44,000 individuals with about 3,000 AS cases. So for a relatively rare disease that's late onset, this is quite a large cohort to study this disease. So again, what we were able to do here is confirm the association with our top variant, which is the RS104 variant. Odds ratios were slightly attenuated, but still strongly significant, with a 30% increase in risk. We were also able to show this is a much more rare variant. This is the minor allele frequency of the first variant is about 7% in the population. The minor allele frequency of this one is about 2 to 3%. So hard to study this one, but because we had such a large sample, we were again able to show that there was about a 30% increase in the risk of aortic stenosis when you had either of these variants. And then when we combined them in risk score, we also were able to show that per allele, there was a 35% increase in the risk of aortic stenosis. What we did then actually is we actually started to say, well, since we have this large group of patients, can we now look at some of these rare combinations of alleles? Can we look at people who have, one RS104 or two RS104s, or one RS104 and one RS379? These are difficult to do because these are rare combinations. And what compelled us to do this was actually we were contacted by the LPA Foundation because they had a 36-year-old woman who she was pregnant when this happened, and she actually went into cardiac arrest while being pregnant, and it turned out she actually had a massive myocardial infarction and was found to have severe aortic stenosis at 36 years old. And they were perplexed about this. So obviously, the good news is that she did fine, the baby did fine. So I'll start with the good news. But then they asked us why this happened. So she actually had genetic testing, and it turns out she, in a sense, lost the genetic lottery. She actually had familial hypercholesterolemia and 2 copies of the RS379 variant. So she actually had both an LDLR mutation and 2 copies of RS379. And no one has ever seen no one knows anything about homozygous RS379. It's so rare. It's only minor allele frequency is about 2% of the population. These people are very, very rare. So they asked us, could you look at this? And I said, well, I don't know if we can try. So when we looked at people that had 2 copies, again, really small numbers. There's only 16 people with this, but 3 of them turned out to be cases. So there was a 4-fold increase in the risk of aortic stenosis if you had 2 of the RS379 variants. So again, in the context of familial hypercholesterolemia and 2 copies of RS379, I think we understand why this 36-year-old woman came close to dying in pregnancy with both an MI and aortic stenosis. So this was actually quite interesting data, both for us and to help inform this patient, the reason behind this patient's condition. Now, what's even more interesting is, there are a lot of risk factors that initiate disease. The question is not, the initiation doesn't always associate with progression. And therefore, if you want to intervene on a risk factor, you need to be sure that it's still an active, a causal player after the disease develops. The number one example of this is smoking and lung cancer. Once you develop lung cancer, whether you stop smoking, the lung cancer doesn't go away or it doesn't stop progressing. So it's very important that you understand whether a risk factor remains active in the disease. And this is not data. This is data from from Quebec City with one of our collaborators, Philippe Barrault, who's a big does a lot of work in aortic stenosis. And these are all individuals with aortic stenosis. This is actually a small randomized trial from several years ago called the Astronomer trial, where they actually gave statins to try to lower LDL to see if it would affect aortic stenosis. And of course, that trial was negative, but they looked to see whether LPA was a predictor of progression. So everyone has mild to moderate AS in this study. And what they were able to show that if you were in the highest tertile of LPA, you had a much higher progression of your maximum velocity across the aortic valve. So the valve was progressively getting smaller, and the resistance of flow was increasing, and therefore velocities were increasing in patients with higher LPA. And when they looked longitudinally over time, they were able to show that if you had if you were in the highest tertile of LPA over time, you had a higher risk of developing symptoms, severe AS, valve replacement, or death if you're in this high LPA group. So again, this actually confirms that not only is LPA important in disease initiation, but it also seems to be a very important predictor for disease progression. And I think this again confirms that LPA, could be a reasonable target to try to prevent progression of this disease. We're in the middle now of working with MESA. MESA has 10 years of data with aortic valve calcium. Everyone's had a scan at baseline, which actually was in that first study I showed you in the New England. And now what we're doing is they've all had a scan at 10 years down the road. So we're actually now measuring the valve calcium 10 years later, and we want to actually see whether we actually see the same type of result with valve calcification, which will be very, very interesting. So I think we've been able to show that LPA is a causal factor for aortic valve disease. It provides a potential novel therapeutic target to prevent valve disease. And I'm sure many of you know LPA, but just very briefly, LPA is this curious molecule which is an ApoB a protein attached covalently to an ApoA. This is what LPA codes for. And people have we don't really fully understand LPA, but it's a cholesterol-rich particle. It does carry oxidized phospholipids. The ApoA component has some homology with the plasminogen, so some people believe that it could also be involved in thrombosis. So using this, we've actually come up with a bit of a model to understand how does LPA lead to calcification. And it's a bit of a crude model, but we're now studying this in a R01 grant that we have, which Mike is collaborating with us on. And so we know that LPA is this ApoA-ApoB complex. And again, this work from Sam Tsimikas in UCSD and Joe Whitstam have shown that most of the lipoprotein-bound OXPL is actually on LPA. So LPA carries oxidized phospholipid. And we know that in certain individuals, genetically, there are some people out there who have a lot of LPA circulating. So people with the RS104 variant have about 30 to 40 milligrams a deciliter higher LPA than people who don't have the variant, and it's similar with other variants as well. So these people obviously have a lot more circulating oxidized phospholipid as well. And one of the interesting things about LPA, and one of the questions people always have is, well, why is LPA there? And it's been thought that perhaps evolutionarily it's been involved in tissue repair, and because it does have these lysine binding domains that avidly bind to denuded endothelium. Now, the leaflets, unlike the vasculature, are highly dynamic structures. They open and close 60, 70, 80, 100 times per minute, and therefore they're prone to more tissue damage and denudation. So it's possible that these areas of denudation act as anchors for the LPA to bind to the leaflet. And so in doing so, they deliver the oxidized phospholipid. And what's really interesting about oxidized phospholipid is in vitro, if you add oxidized phospholipid to either vascular or valvular interstitial cells, they instantly start differentiating into a sort of procalcific phenotype. So oxidized phospholipids are very, very important in this transition to a calcifying phenotype. So the oxidized phospholipid gets delivered to the leaflets, and then the valves start to calcify. So that's something that we're trying to understand using, again, these molecular and genetic method in our grant, and we hope to have some results to show you sometime soon. So what's really exciting about LPA and AS in general is that in 2013 we discovered the importance of the LPA locus for this disease, and then it was validated by a number of different groups. And what's interesting is, completely independently, a number of pharmaceutical companies and biotech companies have been working on developing RNA-based therapies for LPA lowering. So we have no therapy right now to lower LPA. And it's been one of the major impediments to getting people to measure LPA and to actually understand LPA. So there's a antisense RNA that's in phase 3 trials, which shows a tremendous LPA lowering of over 90%. And there's also now a much earlier phase program with an RNA interference molecule, which again shows about 90% lowering. So these would both, allow for the correction, in a sense, of a genetic defect using these RNA therapies. So in 2016, the RNA antisense from Ionis was published in the Lancet. It was a phase 3 trial, extremely potent therapy, LPA lowering by 90% with really no side effects whatsoever. So a very exciting molecule that we're coming to see. And then we're expecting the first RCT. We're not sure if there'll be an AS component. We're trying to convince them to add a AS component to the trial, but there will be a cardiovascular outcomes trial starting in 2019. So we're very excited about this, and we hope that this will eventually be used, as if it isn't in the first phase, eventually be used for aortic stenosis in a subsequent phase. So I'm just going to change gears a little bit. So we identified the LPA variant, and obviously very exciting, and it's made a lot of progress potentially to a clinical application. We're obviously, LPA doesn't explain all of aortic stenosis, so we wanted to know, is there more out there? And now that we had this huge cohort from Kaiser Permanente, we said, let's look for additional variants for aortic stenosis. So this is actually our GWAS of the JERA cohort for aortic stenosis. So this is cases of aortic stenosis compared to controls without aortic stenosis. And the most reassuring thing when you start this kind of work is LPA associated with AS in this new cohort? Because if it's not, the cohort's worth nothing. So it was really reassuring to see LPA by far the top hit here, very, very strongly associated in this cohort. Again, allowing us to proceed and say that whatever we're studying here, because this is ICD coding, these people haven't had echoes, so we did want to be sure that we were actually studying aortic stenosis and not some other noisy phenotype. So this was actually nice to see. But what intrigued us was this variant here. So again, we had nothing that was strongly significant other than LPA, but there was this, in this 10 to the negative 6 range, which we call suggestive association. This has been what we spent the last probably 5 years working on. So what this variant is, it's the RS174547 variant. It actually happens to be in the FADS1, FADS2 locus. That represents fatty acid desaturase 1 and 2. And this is a locus with the two genes next to each other of FADS1 and FADS2. And there's actually an FADS3, which no one knows what it does, nearby as well. Now, going back to basic biochemistry, it's really exciting when you do a GWAS and you end up in a gene you know something about. So in the first time we did it, we've been very lucky because the first time we did our GWAS, we ended up in LPA. So that's nice because there's a lot of stuff that's known about LPA. And we did a second GWAS, now we end up in FADS, which actually is an enzyme in a pathway we know a lot about. So this is great. And again, that is, in a sense, just luck, really. So what FADS does is it actually acts on both either linoleic acid or alpha-linolenic acid, and it converts these omega-6 or omega-3 fatty acids to their long-chain counterparts, arachidonic acid and EPA. So this is actually, these are key enzymes. Linoleic acid is an essential fatty acid, and so is alpha-linoleic acid. And therefore, you do need FADS to perform these conversions. Now, this is where there's a lot of controversy in the field. We do have reasonably good data that EPA is a beneficial fatty acid, and therefore this is likely has good cardiovascular effects. Arachidonic acid is much more controversial. Is having too much N6 and then too much conversion of N6 to arachidonic acid pro-inflammatory? There's some people who believe that, although the data is not very strong to support that. But it's interesting we're in this pathway. So the first question we had is that this pathway is not only involved in arachidonic acid, but it's also associated with a number of different cardiovascular risk factors, including lipids, diabetes, and a number of different factors. So the first thing we did is we said, is this independent of all the known cardiovascular risk factors? So when we adjusted for dyslipidemia, all cardiovascular risk factors, we couldn't make the association go away. So the FADS variant still seemed to be associated with aortic stenosis, regardless of what we adjusted for in the models. So the big question in genetic studies is this worth pursuing? So is this a real finding, or it's only 10 to the -6? Now, for a lot of people, that's like, well, that sounds pretty strong. But for geneticists, it's sort of like, you're still sort of in the weeds, okay? So is this worth pursuing? So the first thing we did, and this is one of the great things about now having multiple data sets, is we went back to aortic valve calcium. And we asked the question, in our first GWAS that we did, LPA wasn't a top hit, but what happened to FADS? Where was FADS? And it was really interesting to see. Now, it wasn't genome-wide significant. It didn't have a crazy p-value, but the odds ratio was like right on. It was like 0.9, the exact same effect we saw with aortic stenosis, a 10% decrease with the minor allele. We saw the exact same effect in valve calcium. Again, now we've gone backwards. We've gone from doing a GWAS in aortic stenosis and seeing if it actually seems to play a role in the biologic process of calcification. And now we're showing that it does. It seems to be important in valve calcification. So this I think, it really got us excited about this. This wasn't just a false positive. There was something real about this finding. So we've now tried to pursue this further. The second big question is, could this all be associated with CAD? Now, CAD and aortic stenosis have a very high overlap. About 50% of individuals have both diseases. So, one of the questions is, could this just be all associated with CAD? When we looked at the largest GWAS of CAD, which is the Cardiogram consortium, the FADS variant was completely flat. So there was actually no signal of an association with coronary disease. So this looked like it was specific for aortic stenosis. It was associated with aortic valve calcification, and clearly here, no association with coronary artery disease. So the big question now in genetics is, we've sort of, shown some validation between aortic stenosis and aortic valve calcification. But is this broadly replicable? You know, it's very important, I think, in genetics, but I think in all science, showing that results replicate and are reliable is key. So we've put together now a number of different cohorts around the world. There's the Quebec City group, which I mentioned earlier, which has about 1,000 AS cases. The Malmo cohort, which I spoke to you about, has 500 cases. This is the Vanderbilt cohort using their EMR, had 760 cases. UK Biobank now is publicly available, so anyone can access this data. There are about 1,400 people with aortic stenosis there. This is the UPenn data set with Dan Rader, has about 1,200 aortic stenosis cases. Epic Norfolk, a smaller cohort with 427 cases, and Umeå in northern Sweden with 218 cases. So we've actually been able to collect about 9,000 aortic stenosis cases and over 300,000 controls to study FADs and hopefully to study additional genetic variants for this disease. So the important thing is that when we looked at FADs across all the cohorts, the results were extremely consistent. So other than these very small cohorts where the confidence are very wide, we saw a very consistent effect in FADs with about a 10% reduction in the risk of aortic stenosis per minor allele for the FADs variant. So again, very replicable. When we actually pool all our results together, we achieve a genome-wide significance of 2×10⁻⁸, which again suggests that this is a robust statistical finding for aortic stenosis. So I think we've been able to show here that a variant, the minor allele of FADs, which actually associates with lower activity of the FADs enzyme, is associated with a reduction in the development of both aortic valve calcium and aortic stenosis. The big question is, how does this work? And I'm not sure. I don't think we've actually fully understood this yet, but we're trying to make progress here. And this is where Mike's contribution has been so important. Mike has measured these fatty acids in all of the MESA participants. These have also been measured in all of the Framingham participants. So we asked the question, we said, well, if we look at N6 fatty acids, and we looked specifically at linoleic acid, and if we looked at N3 fatty acid, and we looked at alpha-linolenic acid, and then when we looked at the long chain fatty acids, EPA and arachidonic acid, and we also looked at the ratio. So the ratio actually is one of the best markers of sort of pathway activity, so of FADs activity. So we looked at the ratio of arachidonic acid to linoleic acid and EPA to ALA. And we asked the question, are these fatty acids associated with valve calcification? So the first thing I want to say is this is actually mRNA expression. This is from GTex, and this actually shows you that if you have the minor allele, you actually have reduction in FADS1, and there's a opposite effect in FADS2. But the net, so although FADS1 goes down and FADS2 goes up, the net effect is a reduction in flow through those pathways. Okay, so there's less. This variant is associated with reduced arachidonic acid and reduced EPA in large studies that have looked at this. So when we looked at this, this is data from Framingham. When you look at arachidonic acid, there's a weak association between arachidonic acid. This was actually in red blood cells and aortic valve calcium. When we looked at the ratio between arachidonic acid to linoleic acid, there was a much stronger. So again, the signal-to-noise ratio improves when you look at the ratios, and we actually saw a strong association for the N6 pathway. Interestingly, and I thought this was actually quite interesting, is when we looked at the N3 pathway, we saw no real effect for EPA, and when we looked at the ratio of EPA to ALA, again, no strong effect. If anything, the effect looked like it was null. So no evidence for an association with any of the omega-3 fatty acids but a relatively strong association for omega-6 fatty acids. And just to clarify, this is actually per standard deviation in change of either the ratio or the metabolite. And what was really interesting is when you actually look at MESA, again, this was done slightly differently. This is actually done, these are plasma fatty acids, but the results were just like so replicable. You almost thought we faked it because the result, arachidonic acid had a 10% increase in aortic valve calcium, the ratio 1.22, and again, no strong effect for the omega-3 fatty acids. And then when we pooled the results together, the results became even clearer to suggest that there seemed to be a very strong association between omega-6 fatty acids, but really no association with omega-3 fatty acids. I think this is really interesting. We know a lot about omega-3 fatty acids, but yet they don't seem to be, at least using these molecular epidemiological approaches, don't seem to be the culprit. There's some suggestion here that perhaps the omega-6 pathway and excess omega-6 metabolism to arachidonic acid might actually be the causal mediator. So this is definitely food for thought and things we're now working to try to address. So the key thing that these data show is that plasma arachidonic acid seems to be a reproducible biomarker for aortic valve calcium. We don't have a lot of biomarkers that seem to track valve calcium, and it looks like LPA is certainly one now, but now it looks like arachidonic acid may be one as well. We still don't have data to suggest that arachidonic acid is involved in disease progression, so this just suggests that it's clearly important in disease initiation. We're trying to generate that data as well. Again, this is all important if we want to try targeting arachidonic acid in studies to try to prevent aortic valve disease. Now the big question is, does excess production of arachidonic acid cause aortic stenosis? So our data sort of suggests this, but it's observational data. It could be confounded. There are a lot of possible pleiotropic effects of the FADS locus. So how can we better address this question? And my lab has developed expertise in this idea of Mendelian randomization, which has been dubbed nature's randomized controlled trial. And what this is basically is it takes advantage of the natural randomization of genetic material to, in a sense, mimic a randomized trial using observational data and genetics. So just to go through this with you, in an RCT, which we're all familiar with, you take eligible participants and they get randomized to an intervention, and this is obviously a drug in most cases, or a placebo, and this changes some biomarkers, some risk factor, and of course in the placebo there's no change. And then what you do is you compare outcomes over time, and this gives you an idea, or at least it proves that the drug actually leads to a clear effect or a causal effect on the outcomes because of the randomized nature of the study. Mendelian randomization is quite similar to that. Here we take eligible participants, and they can be in any cohort study. And what's great about this is everyone's been randomized at conception to a genetic variant. Okay, so we're all in a sense an N of 1 randomized trial. And what we do here is by genotyping, we can identify who got, for example, the T allele and won the genetic lottery, and who didn't. And these individuals, in this case, for example, would have a reduction in the risk factors, for example, LDL cholesterol. There are people out there who have variants who with low LDL cholesterol genetically. And then, of course, you compare them to the individuals who have the sort of common variant, and they have average levels of LDL cholesterol. And then you can compare outcomes. And this has been done for a number of different diseases, including LDL cholesterol. And one of the variants that's been looked in this way is actually PCSK9, and this has led actually to the development of the PCSK9 inhibitors. By mimicking the effect of the PCSK9 variant using a drug, they were able to show that individuals have reduction in LDL and improved outcomes, which actually replicated the Mendelian randomization studies that had been done before. So we decided to do that for FADs, actually specifically for arachidonic acid. So how we do that is we actually take all the variants that have ever been associated with arachidonic acid at genome-wide significance in a large GWAS. So a large GWAS has been done for arachidonic acid. There are many variants that are associated with arachidonic acid with high statistical certainty. There's about 30. These are plotted here. And what you see here is, so we have the effect size for arachidonic acid, and this is the effect for aortic stenosis. So the idea here is that if you have each of these variants can be looked at upon as a singular randomized trial. So when you have a individual who's randomized to this variant, which has very high arachidonic acid, what happens to his risk of aortic stenosis, and you have someone who has a very low arachidonic acid, and what happens to their risk for aortic stenosis. So as you can see, the data is messy. It's not a clear, it's not a very clear association as you see for LDL cholesterol, but statistically, we see an association between variants that lead to higher arachidonic acid and higher aortic stenosis. So there is a trend for that association. And what was really interesting is when we repeat the exact same experiment with aortic valve calcium, so aortic valve calcium now is on the y-axis, we see the exact same result. So again, these are completely separate data sets, completely separate cohorts, and we see a very similar result. So here are the numerical data. Basically what these odds ratios are the slope of that line. Okay, that's how this is done. The slope of that line actually gives you the odds ratio per 5% change in arachidonic acid. So when you do this, you see an 8% increase in aortic stenosis when you do just what we call a standard nonlinear randomization study. When we exclude the FADS locus, so this is actually a big question. And what other than FADS is not there? Because we based the entire project, the entire hypothesis on FADS. It would be great to see a residual association when we look at all the other variants that increase arachidonic acid. So it'd be sort of a orthogonal approach to looking at arachidonic acid. Now, there's some residual association. It doesn't achieve statistical significance, but I think it's at least supportive of these analyses. Obviously, as you can see, are difficult because the power is low, so it's hard to be sure. But there seems to be some effect even when you exclude FADS. And then we do a number of sensitivity analyses, which are statistical, where we try to penalize some of the variants that seem to not follow the line. And again, when we do these type of analyses, we see evidence of association. There's an approach called the Emmer-Egger approach, which is basically a way to address the issue of pleiotropy. And as I mentioned, the arachidonic acid variants are all highly pleiotropic. They do a bunch of different things. And this tries to get at the point of, can we isolate an effect for arachidonic acid? This method, as you can see, is highly underpowered, and it doesn't show us any strong association. So this still remains a question as to how much of this is truly mediated by arachidonic acid versus any of the pleiotropic effects. So we haven't been able to truly say that the effect is mediated by arachidonic acid. What's interesting though is when we do it for aortic valve calcium, the results are very, very similar. We see an association with standard MR, but also with the other type of approaches. And again, we don't see a strong association with this very robust method of Emmer-Egger. So I think the data is at least suggestive. I certainly don't think it's definitive that plasma arachidonic acid may be a cause for aortic stenosis. And what that would suggest, and there is some data that arachidonic acid, when it's, first of all, the arachidonic acid is found in high levels on the valve leaflets. Okay, so when you explant aortic valves in surgery and you look at the valves, they're full of arachidonic acid. Okay, why that is unclear, but this sort of comes together to suggest that perhaps arachidonic acid is where it's supposed to be to have a causal effect. The other thing we know is that one of the metabolites of arachidonic acid in the leukotriene pathway, LTC4, is actually strongly associated locally with aortic valve area. So again, is the metabolism of arachidonic acid to one of these leukotrienes a key step in this process? Is unclear, but there's some suggestive evidence that one of the leukotrienes does associate with severity of aortic stenosis. So, this certainly opens up the possibility that arachidonic acid and downstream mediators are important. I think from a therapeutic perspective, this suggests that could we do something about reducing the effect of FADs and trying to mimic the genetic variant. We only need to reduce FADs a little bit to actually have an effect. We wouldn't want to reduce it or knock it out, because then we would block the omega-3 pathway. But that would be one approach to consider, reducing FAD's activity to try to slow flow to arachidonic acid. But more importantly, perhaps, and this I think is really interesting, that this field that went from aortic stenosis, a degenerative disease of aging, to aortic stenosis might actually have a nutritional component, is could we actually change the way we ingest these fatty acids and the balance of these fatty acids? So we know that in the North American diet, we have a ratio of about 10 to 15 to 1 between these fatty acids. That's changed significantly over the last 100 years, where it was probably at its lowest 3 to 1. And it may be that the excess linoleic acid, if our data are borne out by others, is that the excess omega-6 fatty acids leads to excess flow through this pathway, excess arachidonic acid, and one potential consequence would be aortic valve calcification and stenosis. So, maybe it's time that we all have more linoleic acid in our diet as one approach to try to deal with this issue. So I'm just going to conclude by saying I think I've been able to show you that the LPA locus via circulating LPA levels is clearly a genetic risk factor and a promising therapeutic target. We hope to see more in that area now that there are targeted therapies for LPA. And I think the newer story, which is still not as robust as LPA, is that the FADS variant seems to be strongly associated with AS and ABC. That omega-6 fatty acids clearly are biomarkers for valve calcification, that they may actually be causal for valve calcification, and whether this is a systemic effect or a local effect remains to be seen, and that perhaps therapies targeted reducing either FAD's activity or, more importantly, FAD's precursors might actually prevent valve calcification. So in the future, now that we've pooled all these cohorts together, we're hoping to do a meta-GWAS with all of these collaborators. We're up to about 15,000 aortic stenosis cases, because Decode Genetics has joined us. The University of Nantes from France has a very large cohort as well. So about 15,000 AS cases and 500,000 controls, and they've all been imputed. So we have over 10 million variants to study. So we hope to identify additional variants. And again, our goal is to try to understand this disease, to develop approaches to prevent it. So I'm going to stop by acknowledging a large number of people here in my group. I co-lead a lab with James Eggert, who's a geneticist at McGill University. And most of the work here, actually, I want to highlight is from our fantastic PhD student, Hao Yu Chen, who's really been amazing to bring this all together. And we have a number of different collaborators around the world. It's been really exciting working with these people, it's always nice to collaborate scientifically with a nice group of individuals. So I'll leave you with Ronald Fisher's words. They've influenced me, and I think they position genetics in a special place in biological science. Thank you. Yes.
Thank you very much. That was a very interesting study and presentation. I actually have two questions.
Sure.
Number one, what percent of your aortic stenosis patients are bivalve aortic valves? And number two, to what extent can peripheral blood lipid panels predict the LPA variance?
Okay, so the first question is we try, so we don't have echo data on the large cohort. In MESA, Framingham, the aortic valve calcium cohort, those are population cohorts, so the bicuspid valve is very, very low. In the JERA cohort from Kaiser Permanente, it's possible that patients have a bicuspid. We tried to exclude all mentions of congenital heart disease when we built that cohort. Now it's possible that some patients in there do have bicuspid aortic valve. There's no way for us to actually tease it out. You know, we struggle with this idea. I always say that I think that any process that leads to valve calcification should just probably be accelerated in an individual with bicuspid aortic valve. Now, so I don't think that it would necessarily change the results. If anything, it would actually promote more calcification if you actually had LPA and, for example, a bicuspid. Interestingly enough, I still haven't seen anyone show that people with bicuspid and LPA have faster progression. I expect to see it, I just haven't seen it yet, so it's interesting to see. Now, your second question was...
To what extent can peripheral blood lipid panels predict your LPA variance?
So I mean, if you measure the LPA,
other than measuring the LPA.
Yeah. So you can't. If just with total cholesterol, LDL cholesterol, the usual stuff, you don't have any indication that you have high LPA. Yes.
So arachidonic acid is in a pathway that contains cyclooxygenase downstream, and
right.
aspirin is widely used and blocks that pathway.
Right.
Which blocks the function. So how does the use of that drug affect your modeling and all that?
Right. It's a good question. If aspirin blocked the pathway, it blocks a downstream pathway. So the only thing it could do is it doesn't actually block arachidonic acid. So if by blocking downstream, it could potentially shunt arachidonic acid to another pathway theoretically. So it doesn't actually address the question of whether the aspirin itself is a treatment for aortic stenosis, because that would be a downstream. So COX could be the completely wrong pathway. At least the data so far suggests that it's not the COX pathway. It's actually the leukotriene pathway. So aspirin could be a player here, although I don't think it is, especially in the Framingham Mesa cohort, where the rates of aspirin in these healthy people is actually quite low. So we don't think that it's a major player. Yes?
Going back to your LPA study, I was wondering if anyone's actually been able to figure out the mechanism by which that decentronic variant actually leads to increased mRNA. Is it in cis with some other regulatory element that, as of yet, we're not characterizing, the studies aren't characterizing, or do you think it mechanistically actually has something to do with mRNA level?
So there's some evidence to suggest that those variants are tracking the repeats in the LPA region. So there's these repeats, and we know that they're very hard to study because of the repeated nature and so it's very hard to study. But the people who have done this using proper methods have been able to show that people who have a longer repeats and try to produce this longer mRNA, that mRNA seems to be much less stable, and therefore you get less protein production. So those repeats seem to be key for the protein expression of LPA, and these variants at least partially track those repeats. We know clearly that we get a lot more information about LPA levels if we actually measure the repeats than we do with any of these common variants.
Well, going back to this question the friend you had, so this is there is no alternative splicing involved, there is no increased promoter activity, it's just, so all of these are actually exonic, SMD?
This is actually an intronic SNP. This one, the RS104 is an intronic SNP. It seems to mark these repeats that are exonic.
So then alternative splicing will be
It could be, yeah. I mean, there's been a lot of work in understanding how these SNPs affect RNA expression. Like I said, the best explanation so far is the repeat structure. I haven't seen much on. There's a recent variant that appears to not one of these variants, but there are some rare variants that seem to affect splicing, and have actually very, very large effects on LPA. But this is not one of them. This one seems to track really the repeats directly.
My actually other question was, is there any association between any of these SNPs and other blood tests or blood function tests, like, for example, clotting?
So this SNP is upstream of LPA, and it seems to be very specific for LPA expression. It's never been associated with any other type of phenotype, at least to my knowledge. Actually, it's interesting. The only other place where this SNP appears is actually in statin response. But it's actually very interesting. The reason why that is because if you give people statins, their LDL cholesterol goes down, but their LPA cholesterol doesn't change. So what you see a poor response to statins, but it's actually not a poor response to statins. It's just because statins don't lower LPA cholesterol. So it looks like they're not reducing their cholesterol appropriately, but what it really is because they have a lot of LPA cholesterol in the blood. So it's not a poor response to statin per se, but it's actually related to the fact that they have a high LPA. So these variants haven't been shown to be associated with any other phenotype. They have been looked to see whether they associate with, for example, deep vein thrombosis or other types of thrombosis, and no one's been able to show any effect there. It's interesting, very, very low levels of LPA genetically have been associated with some increased bleeding risk. And again, that sort of has been used to support the notion that LPA is important in tissue repair, and that if you don't have enough LPA, you have a tendency to bleed a little bit more. But that hasn't been totally worked out yet. Sure.
Yeah, fabulous lecture.
Thank you.
Are the data, you have these patients who receive a bioprosthesis of the aortic valve.
Right.
Most of the time they are young, but then you see for unknown reasons that within 2-3 years that bioprosthesis is completely calcified
Right.
again, versus others been around for about 15 years.
Yeah.
Are there any data? Because
So that's a great question, because one of the interesting thing about bioprosthetic valves is that we put them in so we know when the process technically starts. So you could do something preemptively to try to prevent that prosthesis from calcifying. We haven't worked on any. None of our work has looked at bioprosthesis. It's in a sense it's kind of a different animal to a certain degree, but the group in Quebec City has looked at bioprosthesis specifically, and they actually find that ApoB proteins and they have some evidence for LPA and also LPPLA2 to be associated with more rapid progression of bioprosthetic degeneration. So is it something that's modifiable? All these questions are unknown, but certainly an interesting area, because you could potentially put the prosthesis in and look to see who has high risk from biomarkers, and potentially then choose whether they should have a bioprosthesis, whether they should have a mechanical valve. You can make some decisions using this information, but again, a little too early for that yet, but certainly an area that's fertile.
Do you think that some hemodynamic factors play a role too? Because with the aortic valve, you see the calcification. Do you see any change, for instance, with elevated LPA at the mitral valve, or perhaps in the right part system if the valve has to be taken out?
Yeah, so we don't see much with mitral valve disease. The hemodynamic effects are for sure important. I think that's why all the statin trials failed. So I didn't show the data here. We've actually done Mendelian randomization using the LDL variants and shown clearly that LDL and ApoB are causally affecting valve calcification and aortic stenosis. And this, of course, is also supported by the fact that people with familial hypercholesterolemia have a much higher risk of aortic stenosis. So we know LDL is important. The question is when you have to intervene. And if you intervene in someone who has a rock for a valve, there's very little you can do to prevent progression. Now, if you could start earlier, perhaps, there might be some possibility for progression. And I think what happens is once you've developed this highly turbulent flow, then the hemodynamic forces become more important to promote the calcification than the metabolic lipid factors. So I think you need to get in early enough to try to prevent those from damaging the valve to really prevent this disease.
Genetic variants randomly distributed on all these different ethnic groups?
Yes, I mean there are definite ethnic specific variants, which is one of the issues. Now, one of the studies, the study we've done here, has all been done primarily in European ancestry, so we didn't have to deal too much with what's known as population stratification or ancestry differences. But LPA, for example, and Mike and Brian have done some work on the different ethnicities in Mesa and LPA, and there's certainly differences in the allele frequencies of a number of these variants in different ethnicities. But the effects seem to be similar across the different ethnicities. Yes?
So I have tissue questions. So these are calcified. I assume there's a collagen matrix that's underneath it, which implies a fibrotic response, which brings in the destruction of macrophages and myofibroblasts. Are those tissues essentially a chronically inflamed wound that is becoming fibrotic? And where these mediators are all impacting on the activation of the system?
I think that's exactly right. I think this is an inflammatory condition. I think the data with arachidonic acid, again, at least at face value, suggests potentially a pro-inflammatory type of process. Interestingly enough, there's been really interesting data coming out of Scotland where they've actually imaged the valves. So they've used molecular imaging where they've actually given FDG to see how much of it is inflammatory, and sodium fluoride to see how much of it is purely a calcific. So the sodium fluoride actually marks active osteoblastic activity in vivo, and this is done actually in humans. And they've actually shown that there is some FDG uptake in valves, so there is some inflammation, but it's predominantly a calcific process, and the sodium fluoride just glows in these patients.
Early on in the disease, does that change? Does the pattern start off as an inflammatory disease and then becomes?
I don't know if we have the data on that. I can tell you, so in collaboration with a group in Quebec City, we've actually shown, the video is not published, but we actually use the sodium fluoride. We actually wanted to know whether young patients with high LPA, did they have higher sodium fluoride at the valves? So they have normal valves. We wanted to see, like, are they starting to calcify? And interestingly enough, they are. So just having high LPA in 40-year-olds, you're starting to see increased sodium fluoride in people with high LPA as opposed to those without. So again, we didn't do FDG PET, so I don't know. Perhaps there could be even more inflammation at the valve than there is sodium fluoride. So we haven't actually compared, but we do know that early on this process is active, especially in people with high LPA.
Thank you.
Thank you very much.